Good afternoon, class. We are looking at Chapter 5, Integrals, Sections 5.1 to 5.3, the Fundamental Theorem of Calculus, or for short, FTC. We're going to cover the FTC and then the substitution rule. These are basic integration formulas we have seen, and we are adding the FTC. So a quick explanation of that. ddx of the integral of a to x f of t dt is f of x. What this says is, if you integrate with respect to x, because it's f of t dt, this will replace it. And you differentiate it, they undo each other, they give you the function back, meaning differentiation and integration, they undo each other. It's the reverse process. Also, if capital F prime is represented by lowercase f of x, then the integral of a to b f of x dx, which is a definite integral, which is a number, is capital F of b minus capital F of a. Simply evaluate at the endpoints. That's the meaning of it. All right, the method of exhaustion. Areas of familiar polygons such as triangles and rectangles enable us to find the areas of more complicated regions by filling the region with increasingly smaller elements of known area. This is called the method of exhaustion. What do we mean by that? In the old days, when they didn't know the area of a circle, the way they found it, one way was to inscribe polygons. We have a 3-sided, 4-sided, 5-sided, 12-sided. As you can see, when we add to the number of sides, the area of that polygon, it's closer to the actual area of the circle, and that's how they found out. Sometimes they would inscribe and subscribe another one, and they take the average. We're going to use the same concept for the area problems. When we have a function f of x, how do we find the area under this function between a and b and between the x-axis, which is y equal to 0, and the function? So find the area of the region S that lies under the curve y equals f of x from a to b. This means that S is bounded by the graph of a continuous function f, where f of x is larger than or equal to 0, so it is a positive function. The vertical lines x equals a, x equals b, and the x-axis of y equal to 0. Now, this whole thing can be explained right here. S is the following region. Every point such that x is between a and b, y is between 0, the x-axis, and the function f of x. So how do we find the area when we don't have a geometric formula for that? In that case, they come and cut this into so many pieces. For example, right now I cut it in 3 pieces, but in general, this width, we write it as delta x, which is b minus a over n. Now, what is n? N is the number of rectangular strips that we are going to use. So we cut it into 1, 2, 3. In this case, n would be 3. But the idea is that delta x, when we fix it, it's easier for the sake of calculation. Now, how do you find the area of a rectangle? Is the width times the length, or the height in this case. What would be the height? Well, you can go with the left end points, like so. You can go with the right end points, like so. Or you can pick any point in between, and the functional value. That would be the height. It makes no difference. It won't be the area. It will be an approximation of the area. However, clearly, if I cut this into more pieces, the width gets smaller, the approximation gets better. That is the method of exhaustion. As you add to n, the approximation gets better, and eventually when n goes to infinity, becomes the actual area under the curve. For example, we're going to do one here, and before we do that, this summation of I from 1 to n of f of x of I delta x, which is known as a Riemann sum, means f of x of 1 times delta x plus f of x of 2 times delta x plus all the way to f of x of n times delta x, where delta x is defined as b minus a over n. Needless to say, I can factor out the delta x. For example, we want to determine the area between this function, f of x equals x squared plus 1, and the x-axis on the interval of 0 to 2. So what this means is, remember, y equals x squared and shifted up by 1. This is 0, 1. And let's say this is 2. So we are interested in this shaded region. That's the concept. Now we're going to zoom on that part, make it larger so it becomes clear what we want to do. So this shaded region is this. We want to go from 0 to 2. So how do we come up with the answer? Let's go with 4 rectangles. That means we are choosing n to be 4. And so delta x is b minus a, 2 minus 0 over n. The choice is a 4. That gives us 1/2 or 0.5, meaning this is 1, this is 2, this is 3, resulting in 4 regions. All of them have the same width, 1/2. But what is the height? Well, depends which point you want to take. If you want to take this one as your height, that means f of 0.5. We are looking at the right end points. We can continue with all of it. If I want to take this one is the left end point, and I continue with the rest of them, I get all the left end points. If I want to pick any point in between, such as this one, I may have a different area. It doesn't make any difference. It is an approximation. So let's go with the right end points, which is this. And we are not saying this is the area under the curve, we are saying it's close. So in order to find the area for each piece, we need the width, which is fixed at 1/2, and then we need the height. The height for the first one is the f of 0.5 or f of 1/2. For the second one is f of 1. For the third one is f of 1.5. And for the last one is f of 2. So we write R because we are using right endpoints. And then we write R sub 4 because we are choosing 4 rectangular strips. And the answer is delta x, which is 1/2, f of the first point, 0.5, all the way to 2. Now, for example, if I want 1/2, I put it in here, I get 1/4, and 1 is 5/4. If I want 1, square it, you get 1 and 1, 2. If I want 3/2, square it, I get 9/4, and 1 is 13/4. If I want 2, square it, 4 plus 1 is 5. That's how we get those numbers. We plug it in, and we evaluate it, and it gives us 5.75. Now let's do the same thing now, this time for left end points, which means, again, we have the same width, the same delta x as b minus a over n or 1/2. But this time the height for the first one is the height of f of 0. The next one is f of 0.5. The next one is f of 1. The next one is f of 1.5. So again, we plug it into that. Needless to say, f of 0 would be 1 by plugging 0. The rest of them I've already shown you. And so you plug in, and by the way, you can just write 1/2 and factor it out. And so this is what you get. And here's the answer. What I want you to notice is the following. This part repeats here. So it means if I want to calculate this, all I have to do, be careful here. When I calculate this part, I separate it from this. And then when I want to calculate this one, just calculate this one and add this one to it. Now notice, in the case of right endpoints, we are using the right points from A to B. Therefore, A, in this case 0, will not be used. But in this case, for the left endpoints, we start from A, which is 0, and the very right endpoint, namely 2 or B, will not be used here. See? So this is the one that you want to be careful. In this case, f of B is used, f of A is not. In this case, f of A is used, f of B is not. Therefore, the area is somewhere in between. We're going to repeat this, but this time with larger n. Let's go with 8 rectangles. Delta x is b minus a, 2 minus 0, 2 divided by 8, which gives you 2 over 8, or 1/4, or 0.25. Here's the right endpoints. You cut this into 8 equal parts, 0.25, 0.5, all the way to 2. And we go through the same process. It's a tedious process, but this is one way to approximate the area. And delta x is 1/4. This time I factored it because there was not enough room. And again, you plug in 1/4 here, it becomes 1 over 16 plus 1, which is 17 over 16, and you continue with the rest of them. By the way, 2 over 4, 3 over 4, of course, 2 over 4 is the same as 0.5 or 1/2. You do the math, and R8 becomes 5.1875. We do exactly the same thing for the left and the points, and we end up with 4.1875. And again, I want to emphasize the fact that this part is being repeated here, meaning when you want to do this, you really can save some time. And so what happens is that now the area is between these two numbers. And recall when n was 4 was between these two numbers. As you can clearly see, these two numbers are closer. See, these two are closer to each other than these two. So the approximation is getting better and better. And as you add to n, the numbers become closer and closer and closer. And eventually these two are so close, almost identical, and that would be the area. So approximation gets better as n gets larger. And ultimately, when n goes to infinity, it becomes the actual area under the curve. So Riemann sum and the fundamental theorem of calculus, we've seen this already, so let's quickly recap. Suppose a continuous function f is defined on the interval of a to b. If the interval is divided into n sub-intervals so that delta x is b minus a over n, and a sub 0 is a sub 1 is a plus delta x, a sub 2 is a plus 2 delta x, all the way to the last one, b, which is a sub n or a plus n delta x, then the Riemann sum is as such summation of f of x by delta x as I goes from 1 to n is f of x of 1 times delta x plus f of x of 2 times delta x all the way to f of x of n times delta x. So what is x sub I? X sub I is any point chosen in the interval, sub-interval. Remember, you can use the left endpoints, you can use the right endpoints, or anywhere in between. This is an approximation. And as we take the limit of this expression and we let n go to infinity, it becomes the exact area under the curve. So f is a continuous function in the interval of a to b, closed interval of a to b, d dx of a to integral of a to x, f of d dt is f of x. This is one of the FTCs, which simply put means if you differentiate, if you integrate and then differentiate, they undo each other, they give us the function back. This is called a definite integral because this represents a number. The integral of a to b f of x dx is capital F of b minus f of a, and this represents the area under the curve if the function is positive. And it makes this a lot easier when we use FTC. So again, what does this represent? This represents area under the curve as long as f is a positive function. Let's look at this concept of a definite integral, and let's look at each part. This is an elongated S. I've already mentioned that it's an elongated S, which is the integration symbol. Lower limit of integration, upper limit of integration, integrand, the function that we are integrating, variable of integration, also known as a dummy variable, because it is called a dummy variable because the answer does not depend on the variable chosen. The dx simply indicates that the independent variable is x, and that's important to pay attention to. However, this is simply equal to this value, and it's a number, and it's called a definite integral because it's a number and it represents an area under the curve if f is positive, is a positive function. Otherwise, it represents the difference of areas. So the integral of a to b f of x dx is a number. It doesn't depend on x. We could use any letter in place of x without changing the value of the integral. For example, the integral of a to b f of t dt is exactly the same as this one. Or I can change the t to a different variable, f of m dm. So just be careful, these two must be the same. And the approximation is the summation of f of x dx, summation of f of x by delta x as I goes from 1 to n. This is the Riemann sum that it was mentioned. And it becomes the exact or precise if we take the limit and we let n go to infinity. So area is the limit of summation of f of x by delta x as I goes from 1 to n, and n goes to infinity. Let's look at this concept using areas. And if I want to integrate this using areas, first and foremost, I need to know what function I'm dealing with. So let me rewrite that as 1 times dx. You don't have to. If you see that your function y or f of x is 1, which is a horizontal line. And therefore, if you were to draw this horizontal line, we are going to go from A to B. So A to B, B is larger than A. As long as B is on the right side, we are in good shape, because that's the assumption when we write A comma B. And we can find the area of this rectangle, the width, which is B minus A times the height, which is 1. So this definite integral represents the area of a rectangle with the width of B minus A and a height of 1. Therefore, the answer is simply b minus a times 1 or b minus a. Very straightforward. It's a geometric shape we can handle. But I want to look at it from the point of view of definite integral. So you see they give us the same answer. The difference is the definite integral will always work, whereas the shape may not be a shape, a geometric shape that we are familiar with. So I need to write the anti-differentiation of 1 because this is x, the answer is x, and I don't need a constant because this is a definite integral. I'm going to evaluate it from a to b. This is the notation, which means I'm going to put b first, minus, and I'm going to put a second, and that's exactly the same answer. What it indicates that definite integral gives us the same answer as the area. This, we could have done it with geometry, and this we can do it with calculus. Use the signed area interpretation of the definite integral to compute the integral of x dx from -1 to 2. It's important to know that we are not claiming that the definite integral represents the area under the curve. It does it when it's a positive function. Otherwise, it's the difference of areas, as I mentioned before. So notice we are dealing with f of x equals x in the interval of -1 to 2. As you know, y or f of x equals x is a line that goes through the origin. So this is the line. This portion is above the x-axis and it's positive. This portion is below the x-axis and it's negative. And if we want the area that is bounded by this line and a equals -1 and b equals 2, that means we have this portion and this portion. This actually should go up here to 2. This is, I thought I had moved it, so we will fix it in a moment. But this has to go up. In other words, the green portion class is this part. The green portion is this portion, and not this part. Okay. All right. So each one is a geometric shape we are familiar with. It's a triangle, and the area is 1/2 base times the height. Y equals x. So if you look at this point, we have coordinates 2, 2, which means if I want the area for the green one is 1/2 2 times 2, which makes it 2. For the red one, this point has coordinates -1, -1. So for the red one is 1/2. And remember, you look at the distance. So times 1, which makes it 1/2. It's important to know we are looking at the area. And so this distance and this distance, each one is 1. So that's what we have. So we are going to subtract the red area from the green area. 2 minus 1/2 is 3/2. Now, what I'd like to do quickly, I'm going to show you using antiderivative how we come up with the answer and the definite integral, and it works too. So let's look at this function, this definite integral. As you know, the function is x. So when I take the definite integral, I get 1/2 x squared evaluated from -1 to 2. So I can say 1/2 2 squared minus -1 squared. Or you plug in the upper limit first, then the lower limit. As you can see inside the brackets, you get 4 minus 1, which is 3. 1/2 times 3 is 3/2, which is exactly what we got here. We're going to move on. I'm going to ask you to do this at home. I want you to graph and use signed areas to show that this, which means y equals 6x, as we go from -4 to 1, has the answer -45. And that's another thing that shows this is not representing an area, but rather it's a signed area, the difference of areas. That's why it becomes negative, because area is positive. If you were interested in just the area, you would have to put it in an absolute values. So try this, make sure you, and I'm giving you the answer, make sure you can handle this. All right, let's evaluate the integral using the concept we've been doing, which is the definite integral. So starting with the simplest example, x to the power of 7. It's 1/8x to the power of 8, and we don't need a constant. We go from 0 to 1. So you plug in 1, you plug in 0. As you know, 1 gives you 1 to the power of 8, which is 1. 0 gives you 0 to the power of 8, which is 7. So the answer is 1/8. Again, I want you to pay attention to what this says. Even, here's the tip, even if we use another antiderivative, capital F of x plus a constant, in the evaluation theorem, the result will be the same, because the constants here and here, they cancel each other. That's why we don't waste time writing the constant. In which case? In the case of a definite integral. If it's indefinite, we must. All right, I hope you recognize this is 1/x, and therefore the answer is natural log. Now, we put it in an absolute value, and in this case may not make a difference, but you'll see in a moment why it's important to put it in an absolute value. So this is the answer to this. We don't have a constant. We're going to evaluate it from a lower limit to upper limit. So first we plug in 2, ln 2, and then we plug in 1, ln 1, and I hope everybody knows ln 1 is 0. And ln 2 is the precise answer, exact answer, everybody. Now, when we do this, we, in essence, have the same question, part B, for the first part. So it's the natural log. But notice the absolute value for part B wasn't that important, but now it makes a huge difference. And here's the reason. You're going to put ln of absolute value of -1 minus ln of absolute value of -2. If you don't, ln of -1, ln of -2 are undefined. They don't exist. So this is ln 1 minus ln 2. And as you know, ln 1 is 0. So the answer is minus ln 2. What about the integral of sine x dx from 0 to pi? First and foremost, the integral of sine, you remember the derivative is cosine, the integral is negative cosine. So negative cosine x from 0 to pi, again, we don't need a constant. So we are going to put pi and then 0. So we can keep this negative sign, minus cosine x. We can keep this negative sign out, so minus cosine of pi minus cosine 0. As you know, cosine of pi is -1, minus cosine of 0 is +1. So brackets end up being -2. The negative outside makes it +2. So we are looking at definite integrals, which simply put, by the time we are done with them, they give us a number. So here's another example. We know the integration or anti-differentiation of this is 5/3 x cubed minus 4 divided by 2. That means minus 2x squared plus 2x. Since we are evaluating from 0 to 2, I don't need a constant. I'm assuming everybody can anti-differentiate by now easily. So please understand this one, the exponent is 1. Add to it becomes 2 minus 4 divided by 2 is. Now we're going to plug in 2, we're going to plug in 0. I hope you see that since everything involves x, 0 makes it 0. So plug in 2 and then plug in 0, that gives you 0. So all you have to do, evaluate this point. So let's do that. So this is 2 cubed, 8, 40 divided by 3. This is obviously 4 minus 8 plus 4. So we have 40 divided by 3 minus a 4. Minus 4 is negative 12 thirds. With 40 thirds becomes positive 28 thirds. I'm going to move on. Again, even if we were differentiating, the first step is algebra, which means you do this, and that gives you 4v cubed minus 3. That's the first step, algebraic step. Clearly, 4v cubed gives you 4 over 4 v to the power of 4, meaning v to the power of 4 minus 3v from 1 to 2. And pay attention to the variable. Don't change the variable. Otherwise, it will be wrong. So that's the answer. Now let's plug in the upper limit 2 first, minus the lower limit 1 second. So plug in 2, and then plug in 1. Let us evaluate this. This is 16 minus 6. This is 1 minus 3. So the first one is a 10 minus the second one is negative 2. Now we make it plus 2, and the result is 12. We're going to move on. Again, first and foremost, algebraic step. I hope you remember we did this previously, but it wasn't a definite integral. This is already done. You can find it in your notes. This gives you 1. This gives you minus 7 over x. This gives you 2 over x squared. So you make up 3 fractions. And we already did that. 1 gives you x minus 7 times 1 over x. That means minus 7 ln x. And I'm going to remind you what we did for this guy. We wrote it as a 2x to the power of negative 2. And the integration is a 2 over negative 2 plus 1, x to the power of negative 2 plus 1. You can find it in your notes. The denominator is negative 1. So this makes it negative 2 because it's 2 over negative 1. X to the power of negative 1 or minus 2 over x. So again, I just wanted to see how we arrive at minus 2 over x. We have done this before. Again, you can go back to it. Now, let's plug in the upper limit minus, let's plug in the lower limit. So we're going to first plug in number 3. We get 3 minus 7 ln 3 minus 2 thirds. Then we plug in 1, we get minus the brackets, 1 minus 7 ln 1 minus 2 over 1. So we plug in the two numbers. Let's see what happens. So this one, as you know, ln 1 goes to 0, so this is gone. Then we have a 1 and minus a 2. That gives us negative 1. With this negative, it gives us plus 1. So let's repeat the first brackets, and then we add 1. Now, we are adding 3, negative 2 thirds, and positive 1. In other words, we have a 4 minus 2 thirds. As you know, 4 is 12 thirds. Minus 2 thirds makes it 10 thirds. We are done. Now, I'm giving you the exact answer. If you always come up with the exact answer in calculus unless they ask for an approximation. You can put it into a calculator and put it with a bunch of decimals, however many decimals that you have to. Again, we did this for indefinite integral because the independent variable is t. This is t. Remember, the derivative of cosine is minus sine, but the integral is positive sine. So t plus sine t, this time we don't put a constant because we are evaluating from 0 to power 2. Next, we plug in power 2. So this is power 2, this is sine of power 2, minus, this is 0, this is sine of 0. Just plug it. That's all you have to do. Sine of power 2 is 1. Sine of 0 is 0. So the second brackets, it just goes away, becomes 0. And the first brackets, pi over 2 plus 1 is the precise answer. Again, in calculus, we want to answer with precise answer. If they ask for an approximation, you follow it accordingly. We want to evaluate this definite integral, which means first we want to do an algebraic step. Remember, x to the power of square root of x is x to the power of 1/2. With this, x becomes x to the power of 3/2, and this one is simply x to the power of 1/2. So I hope nobody has any problem with that. So again, this is x to the power of 1/2 with this to the power of 3/2. Now, following the power rule, we're going to divide this by 3/2 plus 1 and x to the power of 3/2 plus 1. Over here, 3 over 1/2 plus 1, x to the power of 1/2 plus 1. We don't need a constant because we're going to evaluate it from 1 to 4. And believe it or not, this is it. As far as calculus, now everything is algebra. We're going to simplify and we're going to evaluate. That's all. So first and foremost, this is 5/2 and 5 over 5 halves is 2. This one is 3 halves, and 3 over 3 halves is also 2. So 2x to the power of 5 halves plus 2x to the power of 3 halves, evaluation from 1 to 4. Let's plug in the 4. Let's plug in 1. So first we plug in 4 minus, then we plug in 1. So 2 times 4 to the power of 5 halves plus 2 times 4 to the power of 3 halves minus, now replace it with 1. 2 times 1 to the power of 5 halves plus 2 times 1 to the power of 3 halves. And the first thing I hope everybody notices that this is simply 1, this is simply 1, so this is 2 and 2, 4. This is just 4. 2 plus 2 is 4, right? 2 times 1, 2 times 1. So that's very simple. Now, the next thing I want you to notice, 4 to the power of 5 halves is the square root of 4 to the power of 5, which means 2 to the power of 5, which means 32. 4 to the power of 3 halves means square root of 4 to the power of 3, which means 2 cubed, which means 8. So now I'm going to multiply 2 by this number, 64. 2 by this number, 16, minus 4, right? The second brackets, the whole thing simplifies to 4. And as you can see, the answer is 76. We're going to move on to the next question. Could somebody read this, please?
I can read it.
Please.
Water flows from the bottom of a storage tank at a rate of RT equals 200 minus 40 liters per minute. Find the amount of water that flows from the tank during the first 10 minutes.
Perfect. So we are looking at the rate here, which in essence refers to the differentiation. So the first thing we want to discuss, if capital R of t represents the amount of water that flows from the tank at time t, then the rate of flow is given by capital R prime of t or lowercase r of t, which is 200 minus 4t. Therefore, the amount of water that flows from the tank during the first 10 minutes will follow what we call an accumulated change or net change, which is the integral of this lowercase r of t. In general, the integral of f of x dx from a to b is capital F of b minus f of a, is also known as accumulated change or net change. So let's do that. So the integral of this, the first 10 minutes from 0 to 10. So how do we get those? First 10 minutes from 0 to 10. That's how we get the lower and upper limit, first 10 minutes. Well, this is 200t. This is minus 4 over 2. That means minus 2t squared from 0 to 10. If you plug in 10, You plug in 10, you get 2000 minus 10 squared is 100 times 2 is 200. And if you plug in 0, you get 0, so it makes no difference. 2000 minus 200 or 1800 liters. Why do we put liters as the unit? I want everybody to pay attention to this, because when we go back here, it was liters per minute. That was the rate. Therefore, for the antiderivative, the units are in liters. All right, here's the last question. Could somebody read this, please? Many fish grow in a way that is described by the von Bertalanffy growth equation. For a fish that starts life with a length of 1 centimeter and it has a maximum length of 30 centimeters, this equation predicts that the growth rate is 29 e to the power minus x centimeters per year, where x is the age of the fish. How long will the fish be after 4 years? And they want us to round it to 1 decimal. So, since we're talking about the length, if we let L of x represent the length of the fish at age x, then L prime or dl dx is 29 e to the power minus x, and that's the unit, centimeters per year. So what is the amount of increase? It follows the accumulated change, also known as net change theorem. So the amount of increase in length for the first 4 years, that means from 0 to 4, and then we put that formula. So the amount of increase from 0 to 4 is 29 e to the power minus x dx. And let's evaluate that. We're going to divide this by minus 1, becomes negative 29 e to the power of minus x, evaluated from 0 to 4. And to evaluate this, let's keep the negative 29 intact, and then e to the power of minus 4 minus e to the power of 0. Needless to say, this is 1, so e to the power of minus 4 minus 1 requires a calculator, and then you multiply it by negative 29. And I like to start with a bunch of decimals, okay? And notice this is the amount of increase. But what was the length to begin with? 1 centimeter. That's the initial size. So all you have to do, add these two. And when we add it, then we pay attention to the fact that it says 1 decimal, so we change it to 29.5, because the number next to 4 is 6, it goes up to 5. So we pay attention to everything, and this is it. This is the end of the story. I want to show you a second method to do this. The second method is to find L of x in general first. So we are going to go with this and integrate it without paying attention to 0 and 4. So when we integrate that, we get this one plus a constant, this one plus a constant, because this is a definite integral, this is not. But this is an initial value problem because they said L of a 0 is 1. right? L of 0 is 1. So if I replace this with 0, I get 1. So minus 29 plus C must be 1, and it becomes 30. So again, I quickly show you. If I plug in 0 in here, okay, so L of 0 is minus 29 e to the power of 0 plus c, which is 1, right? L of 0 is 1, and e to the power of 0 is 1. So minus 29 plus c is 1, c becomes 30. And so here's your equation at any given time. At any given time. So what is the question? How long will the fish be after what? 4 years. Replace the x with 4, put it into a calculator. Again, on purpose, I'm showing it with a bunch of decimals, which is exactly what we got here. Needless to say, since we want one decimal, we're going to answer it in this fashion. But I hope you realized both methods work. Use the method you're comfortable with.